Okay, good morning. It's Friday morning. We're going to be going over the homework today, which was table F. I see that a couple people did it. It's good. We'll get some more notes today on solubility, whether something can dissolve and why, and there won't be any homework. Okay, so today's Friday. All right, so I wanted you to do this 10 questions using that chart. So as a reminder, if it's in this side, it will be soluble in water. That means if I put some of it in water, it will dissolve. If it's over here, it's insoluble in water. That means it won't dissolve. But if there are exceptions here, that means that if this is part of it, but it's combined with this, that means it's going to do the opposite of what it is. So an exception over here would be insoluble, doesn't dissolve. An exception over here would be that it is soluble, it will dissolve. It did. All right, let's try it. Copper 2 iodine. So iodine is a halide, and halides are soluble. Is copper an exception? No, it is not. So because of that, it's soluble. Calcium sulfate. Okay, sulfate, right under the halides. They are soluble. Is calcium an exception? Yes, it is. So if it's here, it's soluble. If it's an exception, it's insoluble. I just realized I'm going down instead of across, but that's okay. You have to do them always. Anyways, sodium hydroxide. Hydroxide is here. That means hydroxides are insoluble. Is sodium an exception? Combined with group 1 ions. Well, by now you might know that sodium is in group 1. So this is an exception, making it soluble. Number 7, copper nitrate. Copper nitrate. Well, here's a nitrate. All the nitrates are soluble. There are no exceptions. So this is soluble. That says ammonium sulfide. So sulfides are not the same thing as sulfates. Sulfides are over here. Sulfides are insoluble, and ammonium is an exception. So when combined with group 1 ions or ammonium, so this is an exception. So the exception here, insoluble, makes this soluble. 2, mercury 1 chloride. This is a kind of a tough one. Challenged you on that one. Because this says HgCl. And this, here's the chloride. They are soluble. Combined with Hg. Now you've got to be careful here. This is Hg2. So if I had Hg2 combined with chloride, whoops, it would look like this. It would be HgCl2 because chlorine is a -1 and mercury in this case has a +2, then we crisscross them. So this is HgCl. So HgCl is soluble because that's different. That was a tough one. If you didn't get that one, don't worry about it. Okay, C2H3O2. Here's that, C2H3O2. They are all soluble. There are no exceptions. Is that right? So this is soluble. Magnesium sulfate. Okay, here's the sulfate. They are all soluble. Is magnesium an exception? Silver, no. So they're all soluble. Aluminum oxide. Well, where are the oxides? Al2O3. You know what? I don't see it anywhere. Oxides are not up there. So, this must be a typo. You can't tell by this whether aluminum oxide is soluble or not. So this is a typo, I'll have to change that. And manganese phosphate. Phosphates are insoluble. Is manganese an exception? Manganese is not in group 1. It's a transition metal, and it's not ammonium. So this is insoluble. Okay? 2 more. Yep, 2 more. All right. Potassium carbonate. Well, carbonates are up here. They're insoluble. Is potassium an exception? When combined with group 1, potassium is in group 1, right under sodium. So this is insoluble, but it's an exception. So this is soluble. And the last one is FeBr3, that's iron 3 bromide. Iron 3 bromide, it's a halide, and these are all soluble. Is iron an exception? No. So this is soluble as well. Okay? Hopefully you did pretty well with that. I apologize for that one, and that one was kind of a challenge. All right? All right, so let's go on to our notes for today. Last thing that we learned was the types of solutions. They can be gaseous, they can be liquid. Most solvents are liquid, and most solutions are liquid for that matter. And we have solid solutions, and usually call those alloys. Okay, just as a reminder, if you have 2 things that are the same, like liquid-liquid or metal-metal, the one that has the greater quantity is called the solvent, and the lesser quantity is the solute. Okay, so if I'm taking, for example, if I'm taking gasoline, and I'm only taking a couple of drops of gasoline and putting it in with this lighter fluid, then the gasoline would be the solute and the lighter fluid would be the solvent. All right? So today, I'm just going to learn about a couple things that affect how soluble something can be. So the solubility is a measure of how much solute, remember the solute is the thing getting dissolved, how much solute can get dissolved in a given solvent, and that is temperature specific. So what kinds of things affect that? Well, it's the nature of the solvent. In other words, polar versus non-polar. And we looked at that already, and the term that you should probably keep in your head is like dissolves like. That means if I've got a polar molecule like water, it will dissolve other polar molecules like food coloring. That's one example. Anything that's an ionic substance, an ionic crystal, those will break up into positive and negative ions. So water will dissolve all of that too. So if it's charged, polar molecules will dissolve other polar molecules. Okay, so polar molecules will dissolve polar molecules or charged particles like ions because they have opposite charges. Okay? Temperature. Generally, for solids, an increase in temperature causes an increase in solubility. And you may know this practically. If I've got cold water and I'm trying to make Kool-Aid or something like that, versus warm water, if the sugar and the mix, it's going to dissolve a lot more quickly if I've got it in warmer water compared to cold water. Okay? Now the opposite is true for gases. An increase in temperature causes a decrease. And this should make sense to you as well. In other words, if you have two soda, Pepsi, whatever, if you have two sodas and you bring them home from the store, one of them you open up and leave on the counter. The other one you open up and put in the refrigerator. After a day or so, if you take the one off of the counter that's been sitting out all night and then pour that out, and then compare that to the one that was in the refrigerator, pour that into a glass, which one do you think is going to have more carbonation still? What's the one that was in the refrigerator, right? You know that if you leave soda out uncapped, it will get flat, right? And that flat means that the carbon dioxide is coming out of solution. The warmer it is, the gas, the molecules in there are moving more quickly, and then they essentially force the gases out. So the colder the temperature, the more gases can dissolve. So, example, soda or beer needs to be refrigerated. After opening. The other thing here is what we call thermal pollution. Thermal pollution is when a factory, for example, builds a factory is built on a river or on a lake, and they draw water in from the river or the lake to cool down all their machines. And when they do that, once the water has gone through the factory and heated up, they pump the water right back into the lake or the river. Because of that, hot water or warmer water can't hold as much oxygen, and therefore, when it gets pumped in, the oxygen in the river or the lake, the levels go down. So it makes it harder for bigger organisms to survive, like fish. Okay? So that's called thermal pollution, and it really changes the whole ecosystem of the river or the lake. And the last thing for today is pressure. How does pressure affect solubility? Well, in solids and liquids, there is no effect. In other words, if I excuse me, if I am going to try to dissolve the sugar in Gatorade as a mixing process, it doesn't matter if the cap's on or not. It will not affect how quickly it will dissolve. It's really temperature dependent. However, in gases, an increase in pressure causes an increase in solubility, and vice versa. So the same thing is true of the soda. So we could use the soda as an example as well. Okay? So if I keep the cap on, that's essentially keeping the pressure where it is. If I take the cap off and I lower the pressure, that means the gases will come out of solution. And you've all done that before. If you have a soda and you shake it and then you open it up, you shaking it is causing more pressure inside, and when you release that pressure, all the gas comes out and then it sprays all over. Okay? We don't have to worry about Henry's law. A cap bottle of cola contains carbon dioxide under high pressure. When the cap is removed, how does the pressure affect the solubility of the dissolved? Well, the solubility goes down. A glass of cold cola is left to stand 5 minutes at room temperature. How does temperature affect the solubility? So as the temperature goes up, solubility goes down. Okay? All right, Monday we'll talk about how the rate at which solutes can dissolve. All right? Have a good weekend.